ประกาศให้มันพอถึงนะครับพอถูกกับพี่อันติดพอใจขอลงไปตอนนี้ครับจริงๆแต่ดีนะครับเดี๋ยวนี่อะไรก็ดีเดี๋ยวได้ที่ร้องอ่านก็มีว่า
Good morning. We would like to welcome you to SICMPH 2024 Healthcare Sustainability Syria Conference in Medicine and Public Health. The topics for this morning session are the second Thailand Hub of Talents in Cancer Immunotherapy International Conference, Cancer Immunotherapy, from Promise to Precision, delivering personalized treatment. Please welcome Associate Professor Dr. Mutita Junking and Dr. Neramin Sontayananon.
Thank you for opening for us. Good morning, everyone, and we are delighted to have you here. As you said, my name is Mutita Junking,
and I'm Neramin Sontayananon.
And we will be your MC for this morning session. And to start, we have the open ceremony. Please join me in welcoming Professor Asif Unnanan, Deputy Dean of Academic Affairs, Faculty of Medicine, Sirat Hospital, Mahidol University, to deliver the opening address. Professor, please.
Good morning. Ladies and gentlemen, distinguished guests, esteemed colleagues, and participants. On behalf of the Faculty of Medicine, Sirat Hospital, it is my great honor and privilege to welcome you to the second Thailand Hub of Talents in Cancer Immunotherapy International Conference. This year's theme, Cancer Immunotherapy from Promise to Precision, delivering personalized treatments, underscores the transformative potential of our work in the fight against cancer. At the Faculty of Medicine Sirat Hospital, we are committed to advancing medical research and fostering collaboration among leading experts in cancer immunotherapy. This conference provides a unique platform for sharing cutting-edge research, innovative treatments, and collaborative strategies to move from the promise of immunotherapy to the precision of personalized care. Although our time together today is brief, I am confident that the insights and discussion will inspire new ideas, strengthen partnerships, and contribute to developing more effective and personalized cancer treatments. Together, we can make significant strides in improving patient outcomes and enhancing the quality of life of cancer patients. I would like to express gratitude to working committees whose dedicated efforts have contributed to the success of this event. I wish you all a productive and enriching conference. Without further ado, I hereby declare the second Thailand Hub of Talents in Cancer Immunotherapy International Conference officially open. Thank you.
Thank you, Professor Aziz, for such the warmest greeting. Next, I would like to ask Professor Natia Hirangan, Director of Cancer Immunotherapy Excellence Center from Chulalongkorn University, who also put the another hat as the chairman of Thailand Hub of Talents in Cancer Immunotherapy, to give us a welcoming speech and introduction into the Thailand Hub of Talents in Cancer Immunotherapy, which some of you may have known that, which is the key body who have initiated this wonderful academic gathering today. So please Please join us to welcome Professor Natia.
สวัสดีค่ะ Jane, thank you so much for a nice introduction. And thank you, Associate Dean, for Academic Affairs from Faculty of Medicine, Sirat Hospital, to be the chair of this opening to our exciting event. So I would like to, give you a little bit of background about who we are, especially for the newcomer and from Professor from Korea. So we have, we are just, 1.5, not 1 and 3 months years old. We were born April last year. So this is the initiation from the Thai government, from the National Research Council of Thailand, trying to bring together expert student who working together on the important field. And one of the field that we know can change life and it needs supported from the R&D is in cancer immunotherapy. So that's why we come together and we form this, we call Thailand Hub of Talent in cancer immunotherapy. And this is our logo. So you can visit our website and there are information about how do we come up with this logo. So I wanted to acknowledge here. So now we have 5 universities with us, Chulalongkorn University, Mahidol University, Prince of Songkhla University in the southern part of Thailand, Khon Kaen University from the northeast part of Thailand, and the newest member is Chiang Mai University in the northern part of Thailand. Okay, so this is our goal. I think the main goal is we are, focusing on hospital-based immunotherapy. So, the ultimate goal is we wanted to help each other, implementing this discovery that we have to become a real service in the hospital. So that is our ultimate goal. And last year, in the beginning, we only have 4 party together. So we have the opening launch ceremony with the dean from 4 different medical schools signing together. But as I mentioned, this is just to give you an example of the research center in Thailand that have been doing this kind of research in cancer immunotherapy. So there are 2 research groups at Chulalongkorn University, very big groups here at Sirat Hospital, CCOR CIT, and the stem cell transplant unit from the Prince of Songkhla University, and two center from Khon Kaen University. They also have cell therapy and Khon Kaen Phenome Center. And the newcomer, there's 2 groups, the cell engineering for cancer therapy research group from Faculty of Science, doing mostly like R&D. And also we have Professor Lamnun San here with us, who leads the Center of Multidisciplinary Technology for Advanced Medicine from Faculty of Medicine, Chiang Mai University. And today, the whole day, you're going to be able to listen to some of the work that, our members was doing. And I'm sure this will be inspiring. And this is the forum that we can talk together and, discuss further collaboration. So this is our activities. Each year we get funding from the NRCT to support it. I think one of the goals is we needed to make the database. Because when we wanted to identify people in the field, sometimes we don't know who's working on which area. So I think one of the goals is we wanted to make the website and combine, the information that we have in the small country like Thailand and created a database. And we wanted to share resource and, the discussion. So I think this is a very fruitful things that we have been doing for the past year and continuing to do so. This is the best example of what the event have today. And we are, supporting some travel fund for some student and young investigator to go to have some kind of educational training as well. And at the end, we wanted to kind of, applying for funding together or forming some kind of joint research together. And this is, please check out our website. For those of you who are not, familiar with our website, we have a beautiful website, and we already put in all the names, in here. And we also have, international collaborators. So I would like to welcome Professor to join us, as a member of our international collaborator as well. And this is example of the event that we have been doing. So just, quick recap. We have started the first meeting, national meeting at Prince of Songkhla. So thanks to Dr. Chakravati here, so the Dean of Faculty of Medicine at PSU come to, give us a blessing, and Professor Pietai and I, go there, and we have a great time at Prince of Songkhla. And part of the event is like we wanted to see, the facility and the equipment, because part of the objective is we wanted to share resource. So every time we go, we will visit their facility. So Dr. Chakravati showed us her lab and her, special animal facility that she conducted the immunocompromised mice for the cancer immunotherapies research. And then we have the first international TTCI meeting last year at Chulalongkorn University. Today is the second time. Okay, so yeah, so we have a very fruitful and fun meeting last year. So this is the example of the picture that we took together, and I'm sure this year will be the same. Again, we visit some facility at Chulalongkorn University. And then we went to visit our friend at Khon Kaen University. So this is the very impressive, science park at the northeastern part. And thanks for Ajahn Peach here that come with us. So we be able to see a very, fancy, phenome center that Ajahn Jutharok set up. And he's very kind enough to offer us to do work together. And I think today he's gonna tell us about the newest collaborative work that we plan to do together. And we also visit besides Hub of Talent, Thailand have Hub of Knowledge as well. The northeast part of Thailand have a very unique cancer, which is the big problem, which is the cholangiocarcinoma. So we have a chance to visit the cholangiocarcinoma research institute at Khon Kaen University as well, and also the cell therapy center. So, and then not only to promote that research in terms of basic science or clinical science, part of our mission is to make sure that if we will offer this as a treatment, the clinical personnel is ready. So we have, organized a workshop, and the conference we call Crash Course for Clinical Translation of ATMP. So in this workshop, we are in collaboration with the Faculty of Pharmaceutical Science. And in this workshop, we, gather all the hematologists who are working together to do the clinical part. And here we can see that we have representative from our member joining us. And I wanted to show you that part of the training is not just for research, but we have training for pharmacists and nurse. And this we got the supported from the National Center from Singapore called Actress, which they formed to help, promoting the national guideline of the standard to make sure that we have treated the patient with the with the safety and the best. And now come to today event. So thanks to Professor Pietai and Professor Chanitra, who, kind enough to accept the role to become a chair for our second international TTCI conference today. So I'm very grateful, and I'm sure we're going to have a time to do things together. Oh, I forgot to mention, for those of you who are already our member, please check out our website. We have the member content now. This is a secret among us. You can only, access if you are our member. So basically what it is like, this is kind of knowledge management or knowledge sharing. So when us, going for a conference in, somewhere, we ask them to do the summary of the highlight. And we also share, the activities of journal club together. And because, some of the slide cannot be released to public, so we cannot make this public. That's why we want the login for our student and young investigator to be able to join. And then the last part, I'm very proud that we have now becoming recognized in international society as well. So there's a society called Society for Immunotherapy of Cancer. And within this, they are recognizing the importance of the World Immunotherapy Council. So they formed this called WIC, and they're now focusing more on ASEAN, right? So we have been joining this meeting in Shanghai. I just come back from this, and they're very exciting and give us a lot of compliment that a small country like us can come together and gather everyone together and form a hub of talent. So they kind of recognize us and appoint me to be a committee member. And this is a chair of the WIC. So we are very excited. And actually we have our young, where you are, Dr. Piriya is the representative of TTCI and presented her innovative work, which very impressive. So thanks for that. And my last slide is like, we're going to have a big event. Please join us at the All Fair. It's the whole week, but we're going to have a special forum from TTCI on the Saturday of 27th of July. And in that event, we have invited Medical Council and the Thai FDA to join us as well. So you cannot miss that. So please, come and join us on July 27th. So thank you very much for listening to me.
Thank you very much, Professor Nattiya, for your impressive introduction about the Thailand Hub of Talent in Immunotherapy. So now let's move on to our keynote speaker, keynote presentation. Since he cannot join us lively here, because now he is in the US, Minnesota, so he gave us the video clip for us. And at the end, if the internet connection is good, so he may join us to answer the question that if there is anyone has question for him. So first of all, let me introduce a bit about Professor Richard G. Weil. Professor Weil received his PhD in the field of viral vectors from the Institute for Cancer Research, Chester Beatty Lab. And he was also as a fellow at the Imperial Cancer Research Fund, London, focusing on the biology of metastases, viral vector, and immunotherapies. And currently, he is a consultant at the Department of Molecular Medicine, Mayo Clinic, Rochester, Minnesota, USA. And today, he will present, actually the video clip will present on the oncolytic viruses in cancer immunotherapy, delivering heat or distraction. Okay, so could you please turn on the video clip and present on?
Hello, my name is Richard Weil. I work at the Mayo Clinic in Rochester, Minnesota in the United States. I'd like to thank the organizers very much for the invitation to talk here today. I'm very sorry that I can't be there in person. I would love to come to Bangkok, and hopefully the invitation will still be there, even though I couldn't make this meeting. So as I said, it's a great pleasure to be here. I'm going to talk today about two projects which we are working on in the lab in terms of the immunotherapy of cancer, one in a brain tumor called diffuse midline glioma, and one for liver cancer. So the overall goal of most cancer immunotherapy projects is really to turn these cold tumors hot. What that means is that the tumors which are very poorly infiltrated with immune cells indicate there's very little immune reactivity to those tumors. And we're looking for ways to convert those cold tumors into hot tumors where now they're heavily infiltrated with immune cells. But one of the stories that I'm going to tell you today is that not all heat is equal, and exactly what the nature of this infiltration, this immune infiltration is, matters greatly in terms of achieving tumor rejection. So for many years now, we've been using oncolytic virus to try and drive T cells into tumors. And the rationale behind the use of oncolytic viruses is shown here. The concept is that an oncolytic virus, which is either naturally tropic for tumor cells or has been engineered to be tropic for tumor cells, will replicate in tumors, will lyse those tumors as they replicate, and will kill tumors directly. But perhaps even more importantly, as they are dying, those tumor cells will release tumor antigens in the context of a highly inflammatory local tumor microenvironment induced by the viral replication. And those tumor antigens will be taken up by antigen-presenting cells and presented to CD4 cells and CD8 cells to activate a systemic anti-tumor immune response. So this is the sort of paradigm in the field at the moment. This is what we would like to believe, that oncolytic viruses generate an anti-tumor T cell response. And I think to some degree that's true, but some of the data that I'll show you today suggests that we have to be slightly careful in understanding this mechanism. So my clinical interest is in a pediatric tumor called diffuse midline glioma, previously known as diffuse intrinsic pontine glioma. This is a tumor that grows in the brainstem of children, typically between the ages of about 3 to about 15. It's universally fatal, and full treatment of radiation and temozolomide really extends life by only about 3 months at best. And if you look at this curve here, this is the survival rate at 5 years. Many pediatric tumors have had significant increases in survival. But if you look at DIPG or diffuse midline glioma here, chances of surviving for 5 years are very, very low. One of the big problems with this tumor is that there are very, very few immune cells can be detected within biopsy of the tumor. So it's a very immune silent tumor, and we think that's related to the fact it develops in young children with a very naive immune T cell repertoire. So several years ago, we looked at ways we could try and turn this cold tumor hot. And what we showed was that we could give a preconditioning with cytokines such as GM-CSF, followed by an oncolytic virus, in this case, reovirus. And in those situations where we primed the mice with GM-CSF and then gave intravenous reovirus, we could get very good tumor cures over long periods of time. Based on those studies, which were published in 2014-2015, we started a clinical trial at Mayo Clinic where we gave patients GM-CSF, 2 injections of GM-CSF, followed by 3 intravenous doses of reolysin, the reovirus. We waited for 3 to 4 weeks and then gave a second cycle and possibly a third and fourth cycle. And in this clinical trial where we treated 7 patients, we saw 3 patients did significantly better than we would have expected them to have done based on historical data. Patient 3, for example, here had a tumor which, after the second cycle of GM-CSF and reovirus, appeared to be going away, and was also accompanied by the sort of inflammation in the brain. She had to go into the intensive care unit, the ICU, was given steroids, and within a couple of days was out of the ICU. And is still doing very well. But we saw with the other 2 patients who did very well, we saw this temporary regression, but then followed by progression. So this trial gave us some indication of preliminary efficacy, which was great, but it was clear that more efficacy to be produced. And one way that we thought we could do that is to deliver more virus to the tumor. This is a tumor that's very difficult to inject directly, so there's systemic delivery. So we then investigated work that we've done for some years over adoptive T-cell therapies, and we investigated the value of chimeric antigen receptor T-cell, CAR T-cells, both as an agent of efficacy in themselves, but also as a possible vehicle to carry our virus into the tumor at high levels. So everybody here will know what a CAR T-cell is. Essentially, T-cells engineered to express single-chain FVs, which can see targets on the cell surface of the tumor. And the problem is that CAR T-cells have been very effective in hematological malignancies, but have struggled tremendously against solid tumors, including brain tumors. And the reason for that, we believe, is that there's a highly hostile tumor microenvironment in solid tumors. So even if the CAR T cells can get to the tumor, there are cytokines, regulatory T cells, regulatory immune cells, which really suppress their activity once they actually penetrate into the tumor. So we were interested in whether we could use CAR T cells to carry our oncolytic virus to the tumor, and the release of the virus and the replication would turn this negative tumor microenvironment into a highly inflammatory tumor microenvironment, which could then, we hypothesized, could then increase the activity of the CAR T cells themselves and increase further CAR T cell recruitment to the tumor. So as our model antigen, we used EGFRB3, a unique tumor-specific target antigen, and Laura Ebkin, who was then a postdoc, very talented postdoc in the lab, showed that these CAR T cells do have efficacy against brain tumors growing either in the frontal lobe or in the brain stem. And you can see here a significant increase in the median survival when these mice bear brain tumors, given whole body irradiation and given CAR T cell. But again, we were not seeing any cures in this mouse model, again reflecting that CAR T cell has some efficacy, but not total efficacy, and we need to get improvements. So we tested our hypothesis of whether our CAR T cells, which have some efficacy by themselves, could carry our oncolytic viruses to tumors. We set up mice, we gave them B16 EGFRB3 tumors in the brain, and then after allowing those tumors to develop for 10 days, so it's quite a large tumor, we gave them untransduced T cells, the CAR T cells against EGFRB3, the reovirus by itself systemically, so that's what we did in our clinical trial, or the CAR T cells loaded with the virus ex vivo, and then using these CAR T cells to carry the virus to the tumor. And what we saw was that when we looked at titers of the virus reaching the tumor, obviously if we had no treatment, there's no virus titer in those tumors. When we give reovirus systemically, there was significant amounts of virus actually reaching the tumor, but these titers were not very high. Each of these bars was an individual mouse. Obviously, when we gave the CAR T cells by themselves with no virus, there was no virus. But when we loaded the CAR T cells with the reovirus ex vivo on ice for an hour, and then put those CAR T cells into the mice, we saw increases in titers reaching the tumor of at least a log, and in some cases 2 logs higher, meaning that we could actually use these CAR T cells to deliver oncolytic viruses to these brain tumors at relatively high levels. So we wanted to see whether this translates into therapeutic efficacy. And again, we established a very aggressive tumor of CT2A, these are brain tumor cells expressing the CAR target, injected into the brainstem of these mice. And then we treated them with, again, transduced T cells, CAR T cells, the reovirus by itself, or the CAR T cells loaded with the reovirus. And on day 15, we gave an intravenous boost with the hypothesis that this intravenous boost of virus would reactivate these CAR T cells, which carried the virus to the tumor. And what we saw was really quite dramatic efficacy. So the reovirus by itself really did not increase survival time over the controls. Mice treated with CARs by themselves, either CARs by themselves or CARs carrying the virus but with no boost, significantly prolonged survival but did not really generate any long-term tumor cures. But in this group here, the mice which were treated with the CARs, loaded with the virus, and given this reovirus boost, in this experiment, we cured 5 of 6 of these mice of their tumors in what is a very aggressive model of brain tumors. So we did a lot of correlative studies and we published these results in Science Translational Medicine in 2022, essentially showing that the CARs loaded with the virus were delivering virus to the tumor. The boost with the virus allowed those T cells to be reactivated against tumor, leading to these cures. And when we looked at different time points for the presence of T cells persisting in these mice which didn't get any CARs, did not have any persisting CAR T cell detectable, but mice which had the therapeutic treatment of the CAR T cells loaded with the virus and boosted with the virus showed high levels of T cell persistence in the brain, which we believe is associated with the therapy that we saw, the ability of these CAR T cells to persist, control the brain, find any residual tumor cells and kill them. So these studies, and I haven't got time to go into all the correlative studies, but show that this is clinically very simple. We can co-administer the virus with the CAR T cells, followed by an intravenous boost. So this is fully systemic therapy. We don't have to access these pediatric brain tumors with a needle at all. The CAR T cells make the oncolytic virus better, and the oncolytic virus makes the CAR T cells better. And we've got a lot of data now showing that by loading the CAR T cells with the virus, we induce these memory phenotypes of these CAR T cells, allowing them to persist in vivo. We also showed in that publication that this treatment generates epitope spreading against endogenous tumor antigens. So even as the brain tumors lose the CAR target, there are T cells against endogenous tumor antigens. And as I showed you, the CAR carried oncolytic virus along with the virus boost actually generates reproducible cures without any direct access being required. So the question then comes, I've shown you these sort of preclinical data using EGFRB3 as our model antigen. What tumor antigen would we then target in the case of diffuse midline glioma? And so of various targets that we've looked at, we have sort of come down to looking at B7H3. B7H3 is a type 1 transmembrane protein, and it acts as a co-stimulatory or co-inhibitory ligand, which can either enhance T cell function or in the case of most tumors, is actually an inhibitory molecule and is related to very poor prognosis on many cancer patients, including gliomas, both adult and pediatric. And there's a literature that targeting B7H3 by monoclonal antibodies has shown some efficacy against brain tumors, again, both adult and pediatric. So we were extremely fortunate to have Dr. Supermom visit our lab here in Mayo, and he set out to show whether our DIPG, our diffuse midline glioma cells, express B7H3, and of all of the diffuse midline glioma pediatric cells that we have in the lab, Kay showed that almost all of these tumor cell lines express at very high levels B7H3. We had a commercial antibody and 2 internal antibodies, D10 and F7, which she was trying. So all of our DIPG lines express B7H3, and using these different antibodies, looking at mean fluorescent intensity, these cell lines sort of express different levels of the B7H3, although all of these cells are B7H3 positive. So Kay's work suggested to us that indeed B7-H3 is a very good target for CAR T cell therapy and for CAR T cells to carry virus. And as I say, Kay did a fantastic job while she was working with us, and she made lentiviruses expressing single chain F3s against B7-H3, either this D10 single chain F3 or this F7 single chain. And she showed that she made these CAR T cells lentivirus, was able to transduce human T cells to make these into CAR T cells, and showed that we could kill, for instance, the DIPG13 cell line here. The CAR with the F7 single chain F3 shows very good killing in vitro of both this DIPG line and others. And we saw very good levels of proliferation of the CAR T and their ability to induce interferon gamma. So we're now testing whether these CAR T cells will control tumor growth in xenograft models. And we are writing a protocol ready to use these B7-H3 class to carry replication competent reovirus in combination with these CAR T cells in both adult and pediatric patients. And if the toxicology studies and the efficacy studies go well, we hope that Kay's work will lead to a clinical trial, which we would hope to start somewhere in the first quarter of 2025 of next year. And this is the clinical protocol that we hope we would follow, whereby patients with recurrent either EGFR-B3 positive or B7-H3 gliomas undergo biopsy, treatment with the CARs loaded with reovirus, and then a reovirus boost. So the second disease model, which we're interested in, which I'll show you data for today, is a model of hepatocellular carcinoma. And again, this is what I showed you earlier. This is the paradigm of using an oncolytic virus to kill tumor cells directly, release antigens, stimulate CD4 and CD8 T cells against that tumor. And several years ago now, we used VSV, vesicular stomatitis virus, a negative sense rhabdovirus, as an oncolytic. And VSV is an attractive oncolytic because it's highly sensitive to type 1 interferons. Many tumor cells have defective interferon responses. And so when the virus infects tumor cells and they don't respond to type 1 interferon, then the virus will replicate. But when it infects normal cells which produce type 1 interferon responses, in theory at least, viral replication will be shut down. So we engineered our VSV, which also expresses interferon beta, to increase its safety. That is, when the virus infects normal cells, it will make even more interferon beta and viral replication will be shut down. Whereas, at least in theory, when it infects tumor cells like hepatocellular carcinoma cells, the interferon beta will not shut down the virus because those cells have defective interferon responses. So we wanted to use VSV interferon beta to try and convert very cold, very poorly infiltrated hepatocellular carcinomas into flame tumors. And we did a first-in-human clinical trial with this virus. This is the virus shown up here, interferon beta expressed on the VSV genome. And we treated 13 patients in this trial. And again, there were individual patients which showed real signs of efficacy. This patient was, this is the injected lesion here. And 8 weeks later, we saw very good regression of those tumors. If you notice, this took 8 weeks to occur, suggesting again immune involvement rather than direct oncolysis, because we propose that it takes about 8 weeks to develop this anti-tumor immune response, which then kicks in and starts to clear these tumors. We also saw in a second patient that a tumor nodule, which was not injected with the virus, also underwent regression, again after 5 months, after a long period of time, once again suggesting very much that it's an immune-based mechanism here following oncolysis, which gives these sorts of anti-tumor activity. But once again, of those 13 patients that we treated, a handful of patients seemed to have responses, and so it was clear that we needed to go back to the drawing board and try and increase our therapy based solely on the virus. So we went back into the preclinical models, and we developed with Dr. Paul Monger at the University of Pittsburgh a sleeping beauty model, whereby we inject into the liver 3 plasmids into neonatal mice, encoding the MET oncogene, the beta-catenin oncogene, and the sleeping beauty plasmid, which allows these oncogenes to be distributed through the liver. And by 7 to 10 weeks, we get this multifocal disease in the liver, which replicates many of the features of human hepatocellular carcinoma very well. So we like this model because it's slow developing, develops in presence of an intact immune system, and really sort of mimics the human very well. So when Laura Evkin was in the lab, she stained these tumors for PD-L1 and showed increasing levels of PD-L1 expression in the liver tumors as they developed over time. See here at 4 weeks, there's already evidence of tumor and PD-L1 staining, and by 7 weeks, nearly all of the tumors are expressing PD-L1. So we treated mice in this model with anti-PD-L1 immune checkpoint blockade, and we were very happy that we get about 50% of these mice are cured with immune checkpoint therapy by itself. When we deplete CD8 cells from these mice, this therapy with anti-PD-L1 disappears completely. So this again increases our confidence in this model, because the standard of care now for hepatocellular carcinoma involves anti-PD-L1 therapy. So we have a CD8 mediated therapy here, which mimics the human disease and is dependent upon CD8 cells. And so we followed these mice as they developed tumor by interferon gamma ELISpot assays. We took out spleens from mice at different times, day 21, 28, 49, and then at later time points when most of these mice are dead. And we see that a slowly developing anti-tumor T-cell response, as seen by ELISpot analysis. It's not very strong, and only reaches about 50 spots per well, and then declines with time as these mice progress and die. So there's a very weak anti-tumor T-cell response in these mice. But when we treat them with anti-PD-L1, which, if you remember, gives about 50% cure, now we see that this ELISpot reactivity is sort of similar, but instead of dying away by day 90, now the anti-PD-L1 boosts it significantly in strength. So now we're seeing about 250 spots per 10 to the 6 CD8 cells reactive against the parental liver tumor cells. So anti-PD-L1 therapy is reinvigorating this T-cell response, which in the absence of immune checkpoint blockade dies away, but in the presence of immune checkpoint blockade is clearly boosted to significant level. So then we tested the hypothesis that we could use the virus, the VSV interferon beta virus, to increase the therapy here by making these cold tumors hot and by interacting with the immune checkpoint blockade therapy. But what we saw, and again, this was Laura Evkin's work, we saw this 50% cure with anti-PD-L1 by itself. But when we gave the VSV, instead of increasing the therapy, we saw regularly, despite our hypothesis and despite different timing schedules, we saw a constant decrease in the therapy when we gave the oncolytic virus. So this red line here is VSV along with anti-PD-L1, significantly worse than the anti-PD-L1 itself. So this was contrary to what we thought would happen. And to explain that, we sort of think that there are a lot of things going on. So this is the paradigm, but when the virus infects and kills these tumor cells, as well as releasing tumor-associated antigens, will also release very immunodominant viral antigens. And so we hypothesize that what we're seeing here is that the CD8 cells, which are supposed to be seeing the tumor antigen, are actually seeing the virus. And so if you're a T cell looking for a viral tumor antigen, which in this case is Waldo right up here, T cells looking for the anti-tumor antigens are really heavily distracted by all of this noise here, which are the antiviral antigens. And so T cells, which are looking to be primed against the tumor antigen, are being distracted significantly by the antiviral antigens. So we did CyTOF to test this hypothesis. And these are CD8 T cell populations in mice with just the tumor by itself. When we give anti-PD-L1, which is therapeutic, we see the enhancement of certain populations, such as this cluster 27, which we believe are the anti-tumor T cells, and they're growing selectively consistent with our ELISpot data. But when we add in the virus, this anti-tumor T cell cluster here is almost completely obliterated and is replaced by this highly activated antiviral T cell response. So as the anti-tumor T cell response develops and is enhanced by anti-PD-L1 therapy, addition of the virus generates this antiviral T cell response with the therapy, which is what we saw. Now in our ELISpot assay, here is our anti-tumor T cell response, which sort of dies away, very weak and dies away in the absence of PD-L1. When we add the virus, orange, we see a very strong antiviral response, which weakens this anti-tumor response. Again, when we give the anti-PD-L1 therapy, the anti-tumor response persists and is enhanced, but in the presence of anti-PD-L1 and VSV, now this antiviral response predominates, and this anti-tumor T cell response, which is otherwise relatively strong, is now squashed by the antiviral. So the message here is that clearly not all heat is equal, and we want to make sure that we're generating the right sort of immune heat, which gives everybody sort of a happy feeling on the beach, as opposed to generating this really toxic heat, taking away the anti-tumor. So to try and increase our therapy, we tried to devise a way in which this antiviral T cell cluster becomes also an anti-tumor T cell cluster. And the way that we did that was to encode tumor antigens within the virus itself. So to try and boost these anti-tumor T cells in the liver, we wanted to convert the cluster of highly activated antiviral T cells into highly activated anti-tumor T cells. And so Mason Webb and Tanik in the lab, who's been a fantastic postdoc in our lab from Thailand, made a cDNA library from the tumors which grow in the liver and cloned the cDNA library of tumor antigens into VSV. So now we have VSV expressing multiple tumor antigens. And now, finally, for the first time, we were able to show that when we combine anti-PD-L1 therapy, which gives it some cure by itself, when we combine anti-PD-L1 with the library, the VSV expressing these multiple tumor antigens, now we start to cure these mice long term. So for the first time, we can actually increase anti-PD-L1 immune checkpoint blockade therapy and make it better. And in fact, even just treatment of the virus expressing the antigens, the cDNA library by itself, is also very effective, but is further boosted by the immune checkpoint blockade. And our ELISpot data confirm that again when we treat these mice with anti-PD-L1 and the VSV expressing the cDNA library. Now we still see this strong antiviral response in orange, about 200 spots per 10 to the 6 CD8 cell. But now we also see a very strong anti-tumor T cell response by ELISpot analysis at the same time. So by encoding these tumor antigens in the virus, we are providing anti-tumor T cells which can be boosted by immune checkpoint blockade. And Tanik went on to show that that's consistent with a CD8-dependent therapy. Again, here you see here VSV with a cDNA library treated with anti-PD-L1. These mice are largely cured of their liver tumors. But when we deplete CD8 cells, this therapy seen in the ground here almost goes away completely with this purple line here. It's also slightly dependent on CD4 cells, but not dependent at all on NK cells. So that's, we think now we have a way of increasing these anti-tumor T cells by incorporating tumor antigens within the virus and making the antiviral T cell response also an anti-tumor T cell. And we hope on the basis of Tanik's work to translate this into a clinical trial whereby we use VSV now expressing multiple tumor antigens as well as the interferon beta gene to build on that clinical trial that I about earlier. So overall, our conclusions are that an antiviral T cell response can sort of burn a weaker anti-tumor T cell response. We're not sure whether this is T cell replacement or T cell attrition, and Tanik is working on that. But by converting the antiviral T cell response into an anti-tumor T cell response, we can get really very effective therapy in this liver cancer model. So this is what we would like to believe with oncolytic viral immunotherapy. The reality is, I think we have to understand exactly what is immunological heat. Is it antiviral? Is it anti-tumor? We want to make sure that we get the right sort of immunological heat rather than the sort of wrong sort of immunological heat which burn to tumor response. And when it comes to combining biotherapy with immune checkpoint blockade, the sequencing of these therapies and targeting them is very important. So I'd like to thank you all very much for listening. I'd like to thank the patients and their parents of the patients we treated for diffuse midline glioma and the liver cancer patients that I've shown you today. I'd also like to thank very much Tanik, who has been and currently is a postdoc in our lab, and she's just published this paper in Nature Communications on the HCC model, and Kay, who came over and worked really tirelessly, did a fantastic job on the B7H3 CAR project, and we hope to translate that into clinical trials, hopefully with the beginning of next year. And finally, the rest of the lab and all the collaborators that we have here are shown here. So everybody here contributed to the work. So thank you very much for the invitation to talk. I'm sorry I can't be there in person. Happy to answer any questions. And so, Kakun, thank you.
And actually, Professor is now be with us, but it is Zoom by Zoom online. So because we have a problem here and we are fixing about the Zoom connection with the conference room. So that actually, however, now Professor he is with us for now. So is there any questions or anything that you would like to discuss? Professor Natia, please.
Professor White, thank you so much. I can see you